Hello, my name is Youngjun Ju. I will be presenting our paper called Complete Phase Recovery GAN. In this paper, we propose novel self-supervised inline framework for joint phase rotation and deocclusion. There are two motivations for this research. First, phase-related works improvement, and the lack of high-quality training data. GAN-based frontalization method mainly learn to generate a frontal phase image from profile phase images. Thus, they require image dataset with paired frontal and profile face images. Furthermore, a multiple dataset which is paired dataset is usually used. It leads to generating multiple-like results similar to images in the multiple datasets. 3D-based approaches leverage 3D information as prior information for rotation. Rotate and render do not require paired dataset due to rotate and render operation. They can generate high-quality frontalized or rotated results, but do not consider occluded phased images. Most phase deocclusion methods learn to reconstruct original images from synthesized images occluded with a limited set of objects. GAN can leverage natural facial images, but needs some labels like facial attributes and whether occluded. To address these limitations, we propose complete face recovery GAN called CFR-GAN, which is a fully unsupervised method. Our method comprises three parts. First, occlusion robust 3D-phase reconstruction, and swap RNR, and generate for complete phase recovery. In this training stage, we take both rendered image RES and RPSR generated through the swap RNR framework as input, and then run to reduce the difference between the generated and original images. Simultaneously, our CFR-GAN is trained to recognize the locational information for occlusions raised by interocclusion and self-occlusion. Thus, during the testing stage, our model produced a high-quality rotated and deoccluded image and an occlusion mask. By taking the rendered RPS and RES as inputs, which are rotated only once to the desired pose. First, for occlusion robustness, we do two-stage fine-tuning from our 3D face reconstruction baseline. These results show the effects of our training method in natural occluded face images. Our intuition for swap-RNR is as follows. We first generate two different 3D face with our 3D face reconstruction model. The first 3D face RE is generated from the shape and test parameters estimated through our model. The second 3D face RP is created by projecting pixels of input image onto the estimated 3D shape. Then we coarsely calculate the mask M for the occlusion area. We will explain this in the next slide. Next, we swap the texture between RP and RE for the occlusion area that exists within RP as follows. Finally, RPSR is generated as a broken image through two rotated render operation. And to calculate coarse occlusion mask, we use texture difference and structure difference using CIE relay color space and SIM. We improved the downsampling model of cycle generate to enable the detection and removal of occlusions by adding an occlusion passing path O. The loss function for the generated G consists of 5 loss terms: adversarial loss and occlusion mask loss, occlusion aware reconstruction loss, and perceptual loss and identity loss to preserve identity. This is qualitative results and comparisons with baselines. To evaluate our boosting performance on face-related tasks, we test our method on facial recognition and facial expression recognition. In conclusion, we present the CFR-GAN for joint face rotation and deocclusion, and our occlusion robust 3D face reconstruction model and swap RNR strategy let our model achieve that without any failed dataset. Thank you for listening.